Okay, I think we're going live now. Yeah, I think we're. So let's get started for the second season of Computational Fabrication Seminar. This is the first one of this season and also in the US time zone. We will have two speakers for the topic of textiles, and we will start by introducing our motivational talk speaker, Professor Jim McCann. Jim McCann is an assistant professor in the Carnegie Mellon Robotics Institute. He builds tools that help people make things with the goal of encouraging universal creativity. Jim received his PhD in computer science from Carnegie Mellon in 2010, worked in Adobe's Creative Technologies Lab until 2012. As a full-time independent game developer with his studio Teatro LLC until 2014, and at Disney Research until 2017, after which he rejoined Carnegie Mellon as a faculty. On a lighter note, Jim is one of only two people who have contributed both papers and talks to every edition of Carnegie Mellon's Stroke Conference, SIGBOIC. Now it's in its 14th year. So, yeah, Professor Jim McCann's talk will be on computational fabrication is a perfect fit for textiles. And please take it away.
Okay, thanks for that excellent intro. I'm going to get started talking about how computational fabrication is a perfect fit for textiles. And I figured what better way to start this thing off by trying to justify why this is the most interesting place to do computational fabrication. As the introduction already said, I'm Jim McCann, and you should, of course, feel free to get in touch with me. My details are here and will be on the last slide. So here's the question. Why build tools to help people make things? That is, why do computational fabrication at all? And I have a philosophical answer to that. My philosophical answer is really a philosophical, well, it's a personal answer, but it's this. It's that creativity is my favorite human virtue, so I choose to direct my research toward making it easier to create, trusting this will result in more things being created. If you want people to do something, you make it easier for them to do. And you can see this throughout my sort of research career, from early stuff on painting systems, layering systems, to more recent stuff on fabrication, and even kind of side projects on audio engineering and composition without scales. But for you, and what I'm going to talk about for the next 9.5 minutes, I have a more mathematical answer, a more pragmatic answer. And that's to say that if you have n things to create, each of which takes some amount of effort, E, then research of cost R that reduces effort E to some new lower effort E prime is a net benefit whenever the cost of fabrication, the number of things times the effort per thing, is greater than the cost of fabrication after the research, which is the number of things times this novel new effort E prime plus the cost of the research. So whenever this inequality holds, it is worth it to do the research to make the better tool. And we could fancy this whole thing up. We could talk about amortized effort or modifying E prime to account for utility improvement owing to improved design, but this simple model will be sufficient for the remainder of my motivation. So just some very simple observations about when this inequality is likely to hold. Well, if the number of things to be created is large, then any small incremental improvement in effort will, of course, have a big benefit. And if the reduction in effort is large, then even for a small number of items, this inequality will still hold. And of course, if the research were easy, this inequality would hold. But I think, as we all know, the research is never easy. And just as an aside, I think this shines some light on why one of the killer apps for 3D printing is connecting things, because the number of connectors goes as about n, or about the number of things you have to connect squared. So you have lots of connectors, more so than you have things, and therefore n is large, therefore it's worth investing effort in making those connectors. Some examples down at the bottom here, you see AutoConnect, which synthesizes connectors from geometry and constraints. Parts, which is a system that in part talks about how to make connectors in a parametric way. And FATLab's excellent free universal construction kit, which predates all those research projects and is just a great set of prints for connecting your building toys together. But this number of things argument doesn't just work off in the exotic land of 3D printing. It works right here in the world of textiles as well, because the number of individual textile things you need to design depends on bodies, because textiles often interface with bodies, and it depends on preferences, because people care about what textile things look like. And I would say that in the world, we've got about 8 billion bodies, but we also have probably a fair bit more than 8 billion preferences, because of course preferences, and actually for that matter bodies, do change over time. And I think I've observed people to hold multiple conflicting preferences at once. So that's a pretty big number. And just to head off a concern you might have, you might say, well, wait a second, can't we just dimensionality reduce this? Maybe it just fits along one or two axes, so it's still a simple space. Well, it doesn't. If you look at body scan data like SCAPE, you can see that in the first 4 PCA dimensions, which are what are pictured on the slide here, there's lots of variation, but that variation proceeds on down into the tens, if not hundreds of dimensions. And another way to look at this is every video game that allows character customization has dozens of sliders. And since games are all about getting to good results quickly, you'd think that they would have optimized as well as they could. So even conservatively, if we're talking about the number or the space of bodies and preferences being, say, 10-dimensional, that's still a huge space to design for. There's plenty of things in that space. Okay, so we know that n is big. What about the reduction in effort? Can we make that difference between E and E prime big? Well, in textiles, we can, because textiles fabrication is full of constraints which increase design effort. Just some examples, when you are doing cut and sew pattern generation, you want to think about how any textures on your cloth line up. Or if you're doing knitting, you need to think about the things that the machine can do and not do, what stitches can be stacked, this kind of thing. Or, as you'll see coming up soon, if you're doing paper piecing, you need to think about the ordering of the construction process. Or if you're doing CNC quilting, you need to think about reducing the number of lines that your quilting machine is sewing, ideally down to 1 line. So these are just some examples of the interesting design constraints that systems can help with, and therefore make that change in effort quite large. So in summary, why build textiles tools? Well, because there are many things to be made, because we have unique bodies and preferences, and there's lots of effort to save, because we have a constrained design space. And I guess, since I have a few minutes left, let's talk a little bit about this research cost. Now, I don't propose to save you all of your research costs, but here are a few things I've observed that I think can help as you go out to do textiles research. So here are some strategies for effective textiles research, and this is, of course, opinionated editorial content. Your results may vary. So the first thing I think is really important is to find good low-level abstractions. And that means getting yourself away from specific fabrication hardware and encapsulating just those properties that you care about, like what KnitOut on the left does, that's our low-level knitting machine language, or abstracting away details that are not relevant to your fabrication problem, so you can work at a slightly higher level, like what Jim McCann's excellent stitch meshes work does. Another strategy I'd like to highlight is building high-level primitives. This can be really effective because people can easily adjust the parameters of high-level primitives to get the results they want. So, for instance, in our knit compiler work, and then the knit skeletons work, which I see as sort of a spiritual follow-on that was done over at MIT, tubes and sheet primitives are provided that the users can adjust and connect to build complicated knit objects. Or in the knit primitives work that came out of the University of Washington recently, you can adjust these kind of high-level patches on the surface, which are shaped patches, to get all sorts of variability in your patterns. So high-level primitives seem to be another effective strategy in textiles research. And finally, and I think this one is maybe not used as much universally, is this idea of adapting expert designs and techniques. So you see this a lot in cut and sew pattern sizing or adjustment, where starting with one carefully designed thing, a whole slew of new things can be derived using physics or optimization. So to wrap up my motivation, I think that in textiles, N is big, the change from E to delta E is big, or the change from E to E prime is big, and therefore this inequality holds. So computational fabrication is a perfect fit for textiles. All right, and now I guess we can hand it over to our main speaker.
Okay, thank you very much for the motivational talk. Yes, so our main speaker today is Mackenzie Leake, and I will do the introduction for her. Mackenzie Leake is a mid-year postdoctoral fellow at MIT CSAIL. Her research focuses on building design tools for various creative domains, such as video production and quilt making. She received her PhD and MS in computer science from Stanford University and a bachelor's in arts in computational science and art from Scripps College. Her work has been supported by Adobe Research, Brown Institute for Media Innovation, and Stanford Enhancing Diversity in Graduate Education Fellowships. She is active in modern quilting community and has exhibited her quilts at QuiltCon, Houston International Quilt Festival, and Paducah Quilt Week. Mackenzie, please take it away.
Great. Well, thank you so much for the introduction and for the wonderfully motivating, motivational talk at the start. Awesome. So I am really excited to be here today, and thank you for having me. And today I'll be talking about designing computational tools for modern quilt design. So quilting is this long-standing craft and art tradition that's actually growing in popularity. So today there are actually 7 to 10 million quilters just in the US alone. This is a photo from a quilt show a few years ahead of the pandemic, and it just shows you that it's this very live and active community. And yet, while many people make quilts, it turns out that very few people actually create their own original designs. And while there are some traditional designs that people follow because they have special meaning, such as this wedding ring design, which is typically given as a wedding present, in many cases, quilters simply choose to work from the designs of others. Now, of course, there are many wonderful designs to choose from, such as this daisy pattern, but sometimes there's really something special about designing something from scratch. But in practice, though, quilt design is quite challenging, and very few people, even those with years of experience sewing quilts, choose to undertake this design challenge. And quilt design is challenging because it involves balancing this, kind of the visual design elements with knowledge of the construction process. And now, of course, quilting isn't the only domain in which there's this challenge of navigating materials, tools, and techniques throughout the whole process. And in many fabrication processes, designers need to be aware enough of what the current constraints are to create feasible designs. And they also need to be able to balance the sometimes competing concerns, which can be distracting from the end goal. But it can be hard to know exactly what those various factors are, though. So we could easily collect some different designs, such as these 4 quilt blocks, to see what types of designs people typically tend to make. But this is a bit different than actually identifying the constraints of a domain. So these example designs don't necessarily tell us how challenging a particular block might be to make, how to sew it, or even if it can be made using a specific technique. We don't know if we have another block like this one, if it would be a good design. And to make those kinds of judgments, we need more specificity. We need to actually know what the constraints are. And learning these constraints involves studying a process in detail. And to build tools based upon these constraints, we need to capture the process being performed and characterize it in a way that can be interpreted computationally. And by examining creative processes in detail, we can identify the constraints of a creative domain and use computation to offload certain tedious steps, thus freeing the user to focus on the visual design. And so while we primarily focus on the domain of quilting in this talk, these ideas may also support the design of tools for other creative domains, such as graphic design or ceramics or other types of textile art. And there are many different domains in which we could explore design. So I'd like to highlight first, 2 things that I think make quilting a particularly interesting domain. So first, from a geometric standpoint, quilting offers an application space to explore different types of problems, such as tilings and generative design. And second, quilters already embrace combining tradition and technology, and they use a wide range of techniques in their work already. And a central part of our approach to designing tools is that we need to know a domain very well. And so in quilting, we've been able to do this through reading books and taking classes, and through years of making quilts ourselves. And before we address the technical systems, I wanted to provide some background on a few things that we've learned about quilting so far. So quilting is often divided into 2 main stages: designing and constructing the top, and then sewing the layers together into a quilt sandwich, which is what gives quilts their puffy texture. And computation is becoming an increasingly common part of the quilt making process, but mostly in the second phase of quilting, which is putting the layers together. So for example, computerized long-arm quilting machines automate the precise stitching of the layers together. Some go so far as to stitch an entire quilt with just a few taps on the control tablet, and much of the design process is automated. And there's been some prior work that Jim mentioned earlier in the computer graphics community on helping with this particular part of the quilt process. And there are a few programs for quilt top design, but this existing software is largely designed to support more traditional looking designs and anticipates quilters are going to do kind of all of their planning up front. And in practice, much of quilt design remains largely manual. So in this talk, I will discuss 2 quilting design systems that we have built that support 2 different popular quilting techniques. So first, I'll discuss our work on a tool called Flipper for a technique called foundation paper piecing, and then I'll discuss PatchProv, which is a tool for a technique called improvisational quilting. So foundation paper piecing is a technique for making pieced quilt tops. And in this process, quilters sew pieces of fabric to paper guides. And we learned that many people sew patterns using this technique, but very few actually design them. And to start, we wanted to learn what makes designing these patterns challenging. So each pattern has both the visual design and the sewing order. And it turns out that it's really the sewing order that's the complicated part to develop. And if you draw an arbitrary pattern, it's likely not paper pieceable. So currently, pattern designers use trial and error to identify sewing orders, usually by hand. Unfortunately, this is very tedious, and designers might just give up if no ordering can be found in the first few tries. And these particular design constraints come from the required, precise sewing process, which I'll now outline. So To sew in this way, we start by cutting fabrics to fit over the corresponding regions of the design. We layer the fabrics in a specific way to attach them to the paper, starting by flipping the paper over. And then we place our first fabric over region A1, face up. And then the second fabric on top, face down, along the seam line between A1 and A2. So we layer the fabrics, leaving a 1/4 inch seam allowance next to the sewing line. And this layering process will ensure that the fabrics align with the proper regions while hiding our seam allowances. So next, we flip the stack over and sew along our seam line. And then we just flip our stack back over again. And then fold our fabrics into place. So now both fabrics are right side up. And then we repeat this process of layering, sewing, and folding with the blue piece for region A3. And then we can just tear away the paper, and this leaves us with our complete design. So while the construction process I described led to a precise design, it has some constraints. So these constraints include proper layering, flatness, and no refolding. So if I layer the fabrics in the way that I described previously, the stitching and seam allowances are hidden, and the fabrics are properly oriented in the end. So for example, here we'll see that the red piece is sewn on top of the green piece properly. And this is going to lead to a smooth finished seam. And here I'm keeping the paper and fabrics flat and do not refold any of the fabrics once they're sewn. But if I violate these constraints, I do not properly hide the stitching and seam allowances. So here on the right, I'm going to violate the layering constraint. So I attach the red piece incorrectly under the green piece instead of on top, and this is going to result in the edges of the green fabric becoming exposed instead of hidden. So we know that there are constraints on the construction process, but are there designs that would always make us violate these constraints? So for example, is this design foundation paper feasible? And it turns out that this Y-junction pattern has no feasible sewing order. I tried one order here, but it's not going to work. And it turns out that no matter in which order I sew the seams, I will eventually have to violate our flatness and refolding constraints. And there are many other designs too that would cause you to have to violate these constraints. And it's not immediately clear just from looking at the geometry which blocks are or are not paper pieceable. So for example, if we look at the two blocks on the right here, they look very similar at first glance, except for the seams highlighted in pink. But the top one is not paper pieceable and the bottom one is. And it's not just the geometry of the design that matters. So paper piecing imposes constraints on the sewing order as well. So for this design, you must first attach C and B in either order before attaching A in order to follow the 3 constraints. But note that a design needs to have at least one sewing order to be considered paper pieceable, but many such orders may exist. So when designing a pattern, 2 questions we need to ask are, is a given design paper pieceable? And if so, in what order should I attach the pieces? So to answer these questions, we mathematically formalize the foundation paper piecing process as reachability in a state transition system. We construct a certain type of hypergraph that represents the geometric design and construction process. And we show that a design is paper pieceable if and only if this dual hypergraph is acyclic. So first, let's just take a look at a few definitions that help us prove this main result. So first, we define a paper piecing design as a planar mesh with faces corresponding to fabrics. And then we need a way to describe the sequence of one or more interior edges that border a single face to accurately reflect the sewing process, which involves attaching one face at a time. So we define a seam as the set of all of the interior contiguous collinear edges that border a single face that is not a subseam of any other seam. So for example, here are the seams for this design. And now that we've defined seams, we return to our simpler paper pieceable design. And we want to think about how to construct a dual graph based on this design. So we need a graph structure that captures the sewing process of adding faces one seam at a time. And so in this dual hypergraph, every face is a node and every seam is a hyperedge. And to build our hypergraph, we start by adding nodes for the faces. And then we add an orange hyperedge for the orange seam and a blue hyperedge for the blue seam. So now let's look at a more complicated example of constructing a hypergraph. So we start with adding all of the faces as nodes and identifying our seams. So here the purple seam forms the purple hyperedge, the green seam forms the green hyperedge, and then pink, orange, blue, and finally red. So notice here that each hyperedge corresponds to a single face on one side. For example, the red hyperedge with face D. So now we need one more key element, which are leaf hyperedges, which help us to determine if a graph is acyclic and compute a sewing order if one exists. So here's a design with 5 faces and its corresponding hypergraph. So leaves are hyperedges containing a node that is not a member of any other hyperedge. So in this case, the orange and green hyperedges are leaves because E and D are nodes that belong to just a single hyperedge. So recall our 2 key questions. Is a given design paper pieceable? And if so, in what order should I attach the pieces? So now we can use a greedy leaf plucking process on our hypergraph to answer these questions. So let's take a look at this leaf plucking procedure for a simple block. And here there are 2 available leaves, the blue one with node A and the red one with node C. And we can choose to pluck either of these leaves. And at random, we'll choose to start by plucking C. And now there's just one leaf, the blue hyperedge with node A, so we pluck that. And then B, and then finally D. And the reverse of this leaf plucking order gives us a valid sewing order, which we can then just apply to the pattern. So now let's try another design. So here's its starting hypergraph. And the only available leaf is the blue one with face D, so we pluck that. And we can now look for another leaf, but this time we're stuck with no more leaves to pluck. And if there are no leaves to pluck before the end of this procedure, then that means that the hypergraph contains a cycle and the design is not paper pieceable. So we took these algorithms and then provided an interactive design tool to allow users to create their own designs. And to use the tool, a quilter drags and draws seams, and the tool will indicate if the design is paper pieceable. So here we're starting to draw the planter for a cactus. And now we'll add a seam that makes the design not paper pieceable. So the tool alerts the user to this by highlighting the seams involved in the hypergraph cycle in red. So we can then just adjust the size of the pot to make the design paper pieceable. And the red lines will disappear and the sewing order becomes visible again. And we then just continue adding detail to the design, keeping the design paper pieceable with each additional piece that we add. And then we go on to produce this finished paper piecing design and sew it. And with our tool, we've also generated and sewed several other original designs, like this banana, and this camera, and this house. And using the tool, we also created these 9 leaf designs, which we combined into a full quilt top. And we've also released our code and the tool for anyone who wants to try to generate their own foundation paper piecing patterns. So to learn how a quilter would incorporate our tool into a typical quilt design process, we asked an experienced quilter to work with the tool over a few weeks. So for one of her designs, she started with a sketch, which she was unsure at first how to turn into a paper piecing design. She then used our tool to generate a valid sewing order automatically, and then sewed this design. And she then sewed 3 more blocks and assembled them into a full quilt. So this process shows how developing an algorithm to check for paper pieceability helps us design better tools for quilters that fit within their existing workflow. And offloading the difficult step of computing a sewing order allows the user to focus more on the visual design. So formalization of foundation paper piecing also leads to a relatively simple explanation of the technique that quilters can follow to draft a pattern by hand, even without our interface or the notion of a hypergraph. So it turns out that you can think about the sewing process in reverse. You can imagine starting with a complete design and iteratively removing pieces by cutting along a single seam line. And if you can remove every piece this way, the design is paper pieceable. So for example, we could imagine starting with a fully sewn block. Here we could remove either the blue or the orange piece, since we could remove either with a single cut. So let's remove the orange one first, and then blue, and then green, and then pink. And since we could remove everything, the design is paper pieceable, and if we reverse the removal order, we get back our sewing order. So currently we consider only what are called single section foundation paper pieceable patterns. And some designs like this one are not paper pieceable in a single section. So in our current tool, the user must manually draw section boundaries like these lines in blue before the system will order the pieces within each section. So in future work, we'd like to support starting from a non-paper pieceable design and adding section boundaries automatically, considering both the geometric constraints as well as quilters' preferences toward different ordering criteria. We're also particularly interested in figuring out how to support design using shapes like this pentagon instead of seam lines, and figuring out how to create a paper pieceable design from these shapes automatically. So we observed that many quilters seem to have an intended set of shapes in mind when designing a quilt, and we're interested in exploring when they focus more on the seam lines and the construction constraints, or more on the shapes and the visual design. So, like I mentioned at the start, quilting encompasses a very wide range of different sewing techniques. And before I move on to discussing our other project, PatchProv, I'd like to point out some key properties that differ between these two different quilting techniques. So, whereas paper piecing imposes very specific constraints on construction, improvisational quilting assumes no particular construction method. And whereas paper piecing requires creating patterns ahead of time, improvisational design does not work in this way. It encourages planning and sewing as you go without a fixed design up front. And the end goal differs a bit too. So paper piecing focuses very much on precision, but improvisation focuses more on experimentation and is more forgiving. So now I'd like to talk a little bit more about improvisational quilting in some more detail. So improvisational quilting is one of the most popular techniques that has emerged in the modern quilting community. So improv quilting often results in these colorful, bold geometric designs that can look like some modern paintings. And you might be familiar with the idea of improvisation in other domains, such as music and comedy. And the practice of improvisation emphasizes spontaneity over pre-planning as performers decide on next steps in response to other performers. And there's been some prior work in the HCI community on incorporating these ideas into systems for the performing arts or to support team brainstorming. Now, improv quilting is a little bit different. So in improv quilting, spontaneity is definitely important, but the process doesn't have the urgency of a live performance. So this means that a system to support it does not necessarily require real-time responsiveness and must account for longer-term reflection. So we wanted to know if we could design a system to support this particular design approach. So whereas the process of making a traditional quilt involves following a mostly linear process, starting with a pattern and then creating the sewn quilt, improv quilting is more iterative. So quilters start with some design inspiration and some goals, which are often called a design score, and then cycle through design, cutting fabrics, and sewing the final piece. The finished quilt emerges through these cycles of design and execution. And from reading several popular books on improv quilting, we identified some key properties of the technique and its challenges. And these books help us understand more about this particular improvisational quilting approach. So we learned that in improv quilting, design happens in the fabric. The space of potential designs is very large. Designs result from spontaneous decisions, and process, rather than a complete pattern, is what's valued. And there are also several key challenges to working in this way. So these challenges include getting started, getting stuck, costly experimentation, and recording process. So we set out to design a system called PatchProv to address these particular challenges. So our system needs to assist the user with starting a design, help users avoid indecision, promote reflection, and capture the overall approach or process by which a design is produced. And in PatchProv, we are leveraging the strengths of the digital world to do low-cost experimentation, while preserving the ability to design and experiment as well in the physical fabric. So it's through this connection between the two environments that we are able to record the creation process in the background. But to bridge the digital and physical worlds, users need to take photos of their fabrics as they work. So to use PatchProv, the quilter begins by cutting fabric, working directly in their usual medium. They then load the pieces to create the digital representation in PatchProv automatically. And then they can use this digital representation to cut and lay out pieces digitally without having to waste precious fabrics. And then they can add pieces to this design. So note that as they make changes digitally, items are getting added to the to-do list, which keeps track of this experimentation. And then as the user cuts and sews real fabrics, they can check these items off of the to-do list to make sure that what they see in PatchProv matches what they see in their sewing studio. And then they can see how the design looks repeated by adjusting the rows and columns in the layout guide. So one problem that emerges in working this way is synchronization. So the two representations can become out of sync in two common ways. So first, in cases where the user gets ahead in the physical world, they can just load the new pieces into the system to replace any pieces that are out of date. And second, the user may update the digital representation without cutting or sewing any real fabric. And to keep track of these digital changes, we use what we call a process graph. So our process graph relies on our abstraction of the improvisational quilting process into two operations, cut and sew. And in the physical world, these correspond to cutting and sewing real fabrics. And in the digital world, these correspond to cutting and sewing virtual fabrics in PatchProv. Now, these operations provide no detail about the particular cutting or sewing method, but they capture the overall sequence of steps taken. And essentially here, we build a dependency graph to capture the process of designing and constructing an improvisational quilt. So to build our graph, we start with our input photo of our fabrics, and then we add a node for each cut piece. We will also initialize our to-do list and our done list to keep track of how we traverse our graph. Now, since these operations have already been done in the real world, we mark them as real operations, as shown by the blue highlight. We also add these operations to the done list, since they have been done in the real world. And now in PatchProv, we designate a virtual sew operation by pulling the shapes together and selecting sew. And the yellow highlight indicates this operation has only been done in the digital world. And this automatically adds a virtual sew to the to-do list. So now we decide that we like this design, so we go ahead and sew it in the real fabric. And this means that the sewing operation becomes real, as indicated by the blue labels. And we can now add the sewing operation to the done list. So next we perform a virtual cut in PatchProv, which adds a cut to our to-do list. And then we try out a virtual sew in PatchProv, which also gets added to our to-do list. And note that this operation is grayed out because we need to complete the previous cut operation first before we can sew this piece. So to determine the ordering dependencies between the steps, the system performs a topological sort of the nodes in the graph and determines if the prior steps have been completed in the physical world. We then cut our real fabric, which means marking that operation as real and adding that step to the done list. And now we can move on to the sew step. So we sew the blue square to the gold and pink unit, and we mark the operation as real with a blue highlight on our graph. And we then just move this operation from the to-do list to the done list. And this completes our initial design. So note that at this point, we can just take our done list that we have and see all of the steps that we took along the way. Alternatively, we can continue to explore different variations of this design. So for example, starting with this other branch, we can then add an additional piece and then further build our design. And all of this allows us to experiment while keeping track of changes and not necessarily making permanent changes to our physical materials until we're ready to do so. And we include a visualization of this process graph in the PatchProv interface, which updates as the user makes changes to the design. So to evaluate PatchProv, we invited 4 quilters to create a quilt block in a 2-hour remote study. So they were required to upload at least 1 photo, but were otherwise free to choose their workflow. Here's some examples of the designs that they created. So one participant who tends to make more traditional style quilts laid out her cut fabric pieces for her input photo, then experimented with creating this design in multiples by using the layout guides in PatchProv, and then sewed this exact design. So while she didn't experiment too much with the layout of the block digitally, she did play with the scale and repetition of her block and said that having these steps recorded was very helpful for making additional blocks later. One of our other participants flowed back and forth between design in the digital tool and in the physical materials. So here we see her first input photo with 3 different colors of fabric stripes. She experimented in PatchProv with rotating the strip and adding the red piece along the left border. And then when she went to sew the physical design, she said that she added red to the right side too to add balance. So she took advantage here of being able to make changes in the digital and physical world and have the tool record changes as she went along. She went on to continue working with our tool over several hours and created this beautiful quilt. So we found that PatchProv helped quilters with many of the key challenges identified in improv quilting, particularly low-cost experimentation, with one participant noting, "I've gotten stuck with past pieces, being scared to try anything because I only have this much fabric and I don't want to cut it up." So being able to take a picture of that fabric would definitely help bridge that artist block, but I'm not quite sure how to proceed and my materials are limited. And participants also noted that they liked that the tool records process in the background as they work, both for later reviewing their own process and sharing their designs with others. So one participant said, "The tool comes in handy because then you don't have to remember what you did first and second. This will show you what you did. I think just you could disconnect a little bit and have more fun with the designing of it, knowing that the hard and fast steps are recorded as I work." So improvisational quilting is this very open-ended domain. It can result in stunning works of art like this quilt by Annie Hudnut. And while it's tempting to say that anything goes or assume that it's an easy skill to pick up, quilt book author Raina Gilman reminds us that improvisational piecing doesn't automatically yield good design. So while Patchprob provides support for experimentation and encourages designers to reflect on their process, there are many other visual and physical constraints that the tool just doesn't consider. And an interesting question to explore is how a tool could take a more active role in the design part, perhaps actually even improvising along with the user. So within our discussion of these two systems, we've shown how having a deep understanding of a particular creative technique can enable us to build tools that fit within existing workflows and offload tasks that distract users from making creative decisions. And while we were very focused on quilting in this talk, I'd like also to consider how some of these ideas relate to more general issues in fabrication and design tools. So I think one of the most exciting parts about building these kinds of design tools is learning about and aiming to fit seamlessly into these treasured, long-standing creation methods and traditions. And a different goal is extending these methods and developing new techniques for these communities. And I think it's really important to think about how we can balance tradition and innovation in learning about how these methods have already evolved within the craft community and where they're going in the future. And I also think that there's kind of this interesting balance between what we can learn from process versus what we can learn from the outcome. So by looking at successful, or in the case of this chair, unsuccessful outcomes, we can learn quite a bit about how things are made. But I think we tend to get far richer information by looking more closely at the actual construction process. And this, of course, can be very time-consuming, but if we have better tools for recording and representing the making process, we can learn more about how things are made and better support the creation process. And as we mentioned earlier, the design of physical objects often requires the designer to balance visual design and construction constraints. And this balance shifts at different points in the creation process. And I think a really interesting question for future exploration is how we can build tools that better adapt to these different phases and help the user balance these different considerations throughout the process. And taking a step back, I think we can consider for a moment too why these types of tools are important in the first place. So as you mentioned earlier, design is really challenging, and people tend to gravitate toward working from the designs of others. And yes, of course, there's some fun in coloring within the lines and following the designs of others. There's really nothing like the joy of creating your own original work. But the space of possibilities can be overwhelming when starting from a blank canvas. And I think that design tools can go a long way in helping people start from this blank canvas and gain the confidence and skills to create. And as tool designers, we need to figure out which constraints to embed in the tool and how to direct people's attention to the most important creative decisions. And design is challenging, but making tools that make design easier empowers people to create new possibilities. So with that, I'd like to thank you all for your attention, and I look forward to the discussion and questions afterwards. Thank you.
Okay, yeah, thank you, Mackenzie, for this great talk. I learned a lot about quilting, and it's a very interesting topic. So yeah, if you have any questions, please feel free to post to the YouTube live chat. Right now, I see that there's one question from Amy that she was wondering if you can get away with making designs with a Y junction that is 95% paper pieceable, but the last piece needs to be hand sewn or traditionally pieced, and how that could change the design space.
Yeah, great. Yeah, thank you for the question. Yeah, definitely. I mean, I think that, in practice, there are, yes, different strategies that people will use to maybe paper piece part of the way, and then, like you said, kind of go in and, cheat that last step and sew it by hand. So I think that's, kind of one space of choices, right, is, or just sewing it off the paper, right? So there's that one set of choices where you say, okay, I'm willing to use a different technique, but I want the same design. I think the other set of choices that people sometimes make is, okay, I'm willing to change the design a bit. I'm willing to, move around where the seams are or split it into multiple blocks, but I want to use this technique. So I think that there's always kind of this, this trade-off between, changing the technique and changing the design in those cases.
Okay, great. So there's no other questions in the chat, so I'll try to ask a few. I think it seems that the last bit from your talk on quilting is really related to actually Jim's talk on like there's one category of design tool that will try to utilize existing designs and try to modify them, allow users to do the modifications that conform to some fabrication constraints. Maybe in quilting, it feels like, especially in improvisational quilting, it feels less relevant to have a starting design, but potentially for other types of quilting, there could be like maybe also primitives of quilted patches potentially in design tools.
Yeah, absolutely. I mean, I think that, right, there's this, there, again, it's kind of a looking to the tradition kind of mentality, right, of like, there is this rich space of, named, thousands of named blocks and designs that people have adapted for their own use, that, some of which do have very special meanings or purposes and so forth. And I think, there's definitely, there are plenty of good reasons to use those and build upon those, and there is that tradition. And I think there's, there is this inherent trade-off in supporting these existing traditions like that, or kind of current improvisational approaches, piecing, applique, all these different techniques. And I think it's one set of tasks is really delving into those and helping those particular techniques. And I think there's this other little spot too of, well, are there techniques that people don't currently use that technology can enable and so forth? And I think that's a much harder space of problems to work in. And it definitely still requires going and learning from quilters and so forth. But I think it's really interesting to think about this potential to come up with other designs and tools that extend what people currently do as well.
Nice, thank you. Yes, so I think Amy and Piotr has another question. Maybe Amy's question hasn't finished, so I'll start with the other one. So would it be possible to automatically correct designs to make the graph acyclic? So I think it's for the flipper tool.
Yeah. So I think that, there was we made a decision in the implementation not to automatically correct people's issues, and part of that was, we in practice and how people currently design these tools or design these patterns is that there are many choices of how to correct those, from splitting a design into multiple sections, multiple blocks, erasing a seam and drawing a different one. That there's just there are consequences on the kind of aesthetics for making these decisions automatically. And so we made the choice implementation wise to just kind of highlight where there were problems and alert the user when there were issues along the way, and did not go that next step to break things up. And I think that I think there are pros and cons to doing that automatically, letting people not have to worry about those particular aspects, making an assumption about how they'd want to do it versus giving more of that design flexibility, letting them continue with a bad design further if they want, and not kind of enforcing those constraints necessarily, just making them aware. And I think that's something that is a broader question about these tools and feedback and kind of automation versus expressivity and so forth.
Yeah, that makes sense. So Amy's question is about how much you consider accuracy when designing the patch-proof system. For example, if the user makes the seam allowance too large or the pieces had a gap in the digital design, when you sew them physically, they don't quite fit the way you expected. And how do these accuracy questions impact the workflow of a design? What happens if you expect something to look a certain way and doesn't quite work out as you expected?
Yeah, I think absolutely. Yeah, no, that's a good question, and it is something that definitely did come up. So, Patchprov itself doesn't incorporate any awareness of seam allowances and so forth. Quilters can put things right next to each other, leave a gap, and the tool has no awareness of what seam allowance they're going to use and how they're going to actually sew them together. Now, in practice, for designs that had larger chunks of fabric, that didn't matter too much because that was just a small percentage of the overall area of the pieces. We did actually see this come up in somebody was working with very skinny strips, and they were a bit surprised then when they went and sewed, and the strips got quite a bit narrower. Now, each photo they uploaded again captured that, but it did look different from their original layout. And I think that they're right. There's this. It was funny because the discussion around that was a bit interesting in that they're like, oh well, I didn't expect it to be that way, but I kind of liked it. And I think that there's this fine line between if you're working in an improvisational domain, right, like good surprises and bad surprises, where you might be open to these design changes along the way and expect some element of surprise, but you don't necessarily want to introduce that in the tool, or you don't want it to be introduced by this kind of bad representation, bad linking of representations in the digital and physical world. So I think that's something that in practice would have been a big improvement, and is something that I would definitely be more aware of in future tools that we build.
I see. Yes. So Adriana also has a question about the quilting work. She said, I love how this work enables design iteration while users are iterating on physical construction. It's hard to do because it's generally hard to map from what users can do in the physical world back to computational representations, but it works well in the quilting domain. Can you comment on what makes this work and how you could extend this to other domains? I guess mapping the physical world to computational.
Sure. Yeah. I mean, I think that many of the kind of in a lot of ways, I think these techniques for representing these particular domains, knitting, quilting, whatever, right? Like it does, kind of like Jim mentioned, right? Like there's choices about working with these very low level abstractions or these higher level abstractions, and I think there are tons of opportunities across these domains to find a representation that really works and build tools around what people do. I think maybe the one kind of key piece that I look for in picking these problems, in textiles and in other domains, is really trying to figure out, what's hard, what is the part that is, cognitively most challenging. Are there ways to kind of automate some of these decisions that are maybe less creative or less design focused, where you can have some of that impact of giving people a lot of control over the visuals, but take away some of the tedious elements. And I think that in that regard, right, like many creative domains have those properties of you can ask anybody who makes things and ask them what are the parts that you love doing, what are the parts that are really really tedious and really boring and you would like assistance with, and so forth. And I think that in that regard, right, there's many opportunities for new tools.
Yeah, great. Thank you for answering all the questions. I think maybe there's currently no more questions from the chat, and we will share the current Zoom link that we're using for the live stream, such that interested viewers could join directly and maybe have a short chat afterwards. Does that sound good? Okay. Yes. So I will paste in the link for today's live stream Zoom. Yeah, feel free to join, and I think that will conclude our first computational fabrication seminar, and thank you for coming to the live stream.